Hello physics students. Today we're going to be studying two-dimensional motion. Up until this point we've been studying displacement, velocity, and acceleration for things that are confined to one dimension like a train on a railroad track. Today we're going to look at something that's moving in one dimension and another, like a boat in a river or an airplane flying through the atmosphere when there's wind. So in both those situations, we're just going to look at constant velocity motion. So constant velocity in two dimensions. That's the topic for today. I'm going to begin first by showing you a demonstration I have set up here on the floor. So what I have here is a long sheet of paper, actually several pieces taped together, and my nice trusty bulldozer here. And I have Betty Rubble helping me in this little experiment. So imagine instead of this being a piece of paper, this is a waterway. And so this then would not be a bulldozer, but a boat. So use your imagination, little boat waterway. And what's going to happen is someone's going to be in this boat and they're going to try and get across the river to the other side. And this time, this waterway in this experiment or demonstration, the water will be stationary. So that's really easy. You just, the boat turns on the motor, and at the same time, Betty is going to start the time and time how long it takes this boat to cross the river. And gets about 4.25 seconds. So nothing too complicated, not too surprising that the boat landed on the shore on the opposite side because that's where it was pointed. So now what we're going to do is see what happens, how that motion changes if the waterway is actually moving. So what I'm going to do is I'm going to reset the timer, and this time we're just going to pretend that Betty's timing it because there's too much that's going to be happening for me to do. But what I'm going to do is turn this on, and when it gets onto the paper, I'm going to start moving the paper to the side. That would represent the river flowing this way. And we're going to see what happens to the motion now instead of being straight across. Okay, so let me start this up. Okay. And now the river is flowing, and you see that the boat landed over here. And if we would find that if Betty timed it, it would still take 4.25 seconds, but the boat ended up off course. It left here. Instead of ending up directly across the river, it's now downstream a little bit, so the water pulled it across in the same amount of time. So that's the phenomenon, the moving boat in a moving medium, the waterway. What we're going to do is now move to the chalkboard, and we're going to see how we could analyze this, figuring out possibly how far this ended off downstream, maybe what angle it went off at with our physics calculations. So let's move to the chalkboard. Okay, so there's the title for today, Two-Dimensional Motion, Situations where the acceleration is zero. So let me pause the video and give you a chance to jot this down. Okay, so just like in our demonstration that we just saw, we've got a river, in this case 50 meters wide, that's flowing 4 meters per second to the east. We've got a park ranger rowing 5 meters per second to the north. We're to determine the net velocity and the angle off course with respect to the north direction. Also the time to cross the river and the distance downriver, sort of off course after the crossing. All right, so let's jump into part A, the net velocity and the direction. So let me pause the video, give you a chance to jot this down. Okay, so here's our 50-meter wide river, the velocity going to the east, the boat going 5 meters per second to the north, and then, of course, pulled off course like this, we're going to land over here. For part A, we want to find the net velocity. So what we have to do is add the velocities, but as vectors, because they're vectors. So with numbers, you just add. 4 plus 5 is 9, right? But in this case, we have to see that these are 90 degrees to each other. So we can either draw them like this and make a parallelogram and draw the diagonal, or do what I've done, put them head to tail. I draw the 5 first, and then the 4, I don't draw down here. I start drawing it where the 5 left off, this way. And then the net motion, it's kind of intuitive, It's from the beginning of the first arrow to the end of the last arrow. That's the net velocity and the direction. So as you can see, we've got a right triangle. We've got to use the Pythagorean theorem. But in the Regents, you always have to write the formula, plug in the numbers with units, and solve. So that's what I've got here, formula, my two velocities, and then the answer, 6.4 meters per second. I'll pause the video. Oh, I already paused. Okay, so that's part A, velocity net. Now we've got to figure out the angle from the north direction, this angle right here. So let me erase this, make myself some room. Okay, so if you look at this triangle, we know this side and this side. This is the opposite side, this is the adjacent side. And we're looking for the angle. So the trig function that relates opposite and adjacent is the tangent function. So once again, I've got to begin by writing out the formula. So I'll just put this for opposite and this for adjacent. Second step, I've got to plug in the numbers with the units. So I could do it on the next line, or if you want, you could do it by continuing the calculation perfectly fine. So the opposite side is the 4 meters per second. And the adjacent is the 5 meters per second. Notice that the meters per second go away, and that just leaves me 0.8. So tan theta is 0.8. In order to figure out what theta is, I've got to take the inverse tangent of both sides. So if I take the inverse tangent of tangent, that just gives me the angle. And then tan to the minus 1 of 0.8 is on this side, because I took inverse tan of both sides. If I put that on my calculator, punch it in, I get 38.7 degrees. Okay, so I have my net velocity and direction, or my speed and direction, that's velocity. I got part A done. Part B, what I want to do is now figure out the time it takes to cross. So what I have is I've got velocities and displacement. And the formula that relates those is, and don't write this down just yet. This is right off the reference table. So in this case though, as I said, there's no acceleration. We have the water flowing at a steady pace, the boat going at a steady pace. So this is 0. And just like in the free fall problems, very often when v initial was 0, when something started from rest and accelerated, we could leave this part of the formula off and just write d equals 1/2 at squared and lose no credit at all. So in this case, if acceleration is 0, we could not even write that and just write this as a formula, full credit. So why not, right? All right, so go ahead and we're going to continue on. So the distance we have, the displacement, is 50 meters, okay? 50 meters. I'm going to leave this blank, and the time is what we're looking for. Now, we have 3 velocities right now. We have 5, we have 4, and we have 6.4. Which do we plug in? Let me pause the video and give you a chance to think about it, okay? What did you say? If you said the 5, you're correct. A lot of people would put the 6.4 here. Why the 5? Well, the 50 meters is going in the north direction. Why would we plug in an east velocity or a northeast velocity? Doesn't make sense. If you've got a north direction displacement, you've got to use a north direction velocity to be consistent. Okay, so we use the 5 to find the time. This is easy. We don't even need a calculator, just 10.0 seconds. Okay. Part C. How far downstream, off course, did this park ranger end up? This distance, that's what we're looking for. Okay, so let me make a little space. Maybe that's enough. And by the way, I got to pause here to give you a chance to jot that down, so I'll pause now. Okay, continuing on, part C. Once again, we could just write d equals VIT. Because the acceleration is 0, we could leave it off the formula. Now, we know the time is 10 seconds. What velocity do we plug in? Do we plug in the 4, the 5, or the 6.4? I'll pause and give you a chance to think about it. Well, what did you say? If you said the 4, you're correct. We want to know how far downstream in the east direction. So we've got to use an east velocity to be consistent. That's the 4. Okay. Solving that out, real simple, 40 meters downstream. Okay. Let me pause to give you a chance to jot that down. Okay, I want to do a little bit more. What if we had the park ranger going 5 like this, 4 like this, ends up going this direction, but this time there's a waterfall right here. Well, not so good. Park ranger goes off the waterfall. What if we wanted to correct and not go downstream, but end up directly across stream? Now, to see that happen, what I'm going to do is set up and go to the paper demonstration I had to show you that in action, how we could correct to make that boat not drift in the east at all, but just go directly north. All right, so let's take a look. Okay, so as we saw in the previous demonstration, if I angle the boat straight across and there's a river current, then the boat ends up going like this. And we want to now correct and turn the boat in such a way that we no longer drift down current like this. So what we'd obviously do is turn the boat like this, some proper angle, and then we'll see that when I do that, the result of the boat's motion plus the river's motion ends up being straight across motion. So let's take a look. Okay, so as you saw, the boat's going like this and the river's going like this, and so it's going, the net motion is like this and it ends up over there. So let's go back to the board and see how we could figure out that angle of compensation. All right, so this is the problem expressed in words. Determine the correction angle for the Ranger to go straight north, as we saw with the paper and the battery car. How much do I have to turn this upstream? Now, what a lot of people will say is this, and it's incorrect. They'll say, wait a minute, this park ranger is pulled 38.7, I put 39 here, off course like this. I know how to fix it. I'll just turn 38.7 upstream and then it'll fix it. And it's not actually correct, okay? Let me show you why. In order to figure out this new angle, we've got to draw an entirely new triangle. Because what we're doing is we're taking this 5 and it's no longer going to go in this direction. We're going to tilt the 5 over in this direction. So I'm going to go like this, 5 meters per second. And I tilt it so that there's the north direction. Just far enough so when I add the 4 to the 5, I end up directly back on the north direction reference line. So the net motion or the net velocity of the boat is now like this. See, V net used to be the hypotenuse. The 5 and the 4 used to be on the legs. Not anymore. The 5 now moves to the hypotenuse. This stays on one of the legs. This is now a new leg. So it's all different angles because the triangles are not similar. So this is the angle I'm looking for. What I have is the opposite side and the hypotenuse. So the trig function that will allow me to calculate that is the sine function. So I could say sine theta is opposite over hypotenuse. Kind of running out of space, so I'll continue like this and say 4 meters per second over 5 meters per second. That divides to 0.8. So now instead of doing inverse tan of 0.8, I'm doing inverse sine of 0.8. And that comes out to be about 53 degrees, okay? Different triangles, different angles, okay? So 53, you go 39 off course. To fix that, you have to go 53 upstream, okay? And I just want to point out one other quick thing. But before I do, let me pause to give you a chance to jot that down. Okay, so we could also find the V net, and just to speed things up, I'm not going to write out the formula, but we could find that V net by using the Pythagorean theorem. And now V net is not the hypotenuse, it's one of the legs, and that comes out to be exactly 3 meters per second. Okay? All right, so let me pause to give you a chance to jot that down. I want to make a couple final points. This also applies to airplanes with wind currents. We could have had a plane going 500 meters per second north, wind 400 meters per second east, and then all the calculations the same. Another thing about correcting. So planes, when they're trying to land on a runway, they have to correct for the wind. I remember when I was a kid, and one of the first times I saw planes landing at an airport, I thought the pilots were making a mistake. They were coming in for a runway, and rather than the plane being straight like this, it was crooked, and it was coming in. I said, what a terrible pilot. He's flying the plane crooked, right? Instead of going straight like this, he's going like this, and he's going straight north. And I didn't realize what he was doing is he was turning to correct for the wind because he didn't want to land like this in the bushes, right? He wanted to go on the runway, so he had to go like this, so he drifts along parallel to the runway, so the plane was crooked. So planes have to correct certainly when they're landing. Another point I want to make is that this has something to do with safety also. If the current is bigger than the velocity at which something can move, you cannot ever correct for the motion of the water. Like, for example, if the river flowed 6 meters per second, there's no way to make 5 a hypotenuse to drift directly across the river. No matter what, your boat is not fast enough, it will always get pulled downstream, okay? This could have real serious consequences, particularly at a beach. Sometimes you may have heard of rip currents. Water flows incredibly fast away from the beach. And say it flows 10 meters per second and a human can swim 2 meters per second. What happens is there's no way to correct for this. In fact, if you swim 2 meters per second directly at the beach because you're panicking, you're getting pulled out into the ocean, you look out there, there's nothing but Atlantic Ocean, right? So you feel you're going to drown, so you panic and you swim toward the shore. The water's 10, you're going to drift while exerting all your might. You're still going to drift at 8 meters per second out into the ocean. You cannot beat the rip current if you are trying to go directly into shore. The real way to do it, the way to beat a rip current or rip tide, is to swim perpendicular to the current. So you swim 2 meters per second like this, and the ocean pulls you 10 this way. And you're being pulled along a diagonal like this. And it may be very scary because you're still being pulled out into the ocean. But eventually, you end up out of the rip current, and then you turn and swim back in. But you never try and fight it. You just swim parallel to the beach and let yourself get carried like this until you get out of that current region. So it's because you cannot correct because the water's faster than you. So you just have to kind of go with it till you get out of that rip tide. All right, so that's 2D motion. Remember, we create right triangles. You put the boat velocity, the river velocity, Pythagorean theorem, and tangent function. When you figure out how long it takes to cross the stream, you have to use the width of the river and find the velocity that's parallel to it. So the velocity and the displacement have to be in the same direction. Same when you want to find out how far off course. You've got to use this, to find this displacement, you've got to use that velocity. So that's two-dimensional motion, a boat moving through water or a plane moving through the air. So that's it. I'll see you in the next physics video.